Greetings, welcome to this new video about superposition theorem. Solve the problem number 15. In this video, I will demonstrate the application of the superposition method to solve a problem, and I will guide you through the step-by-step process of using superposition to solve the problem at hand. Let's consider this network consisting of 5 resistors labeled R1 through R5 as well as 3 independent sources. The question now is to use superposition method to find the voltage Vx across the resistor R3. Let's move on to the solution. First, we begin by identifying each independent source in this circuit. This step provides a clear understanding of the source that will be analyzed separately. In this circuit, we can observe 3 independent sources. One independent current source Is and 2 independent voltage sources Va and Vb. Next, we proceed to deactivate all but one independent source in the circuit. This involves replacing the inactive voltage source with a short circuit, which means it's 0 voltage, and the current source with an open circuit, which means it's 0 current. First, let's begin by activating the independent voltage source Va and deactivating the independent current source Is and the independent voltage source Vb, which will be replaced respectively by an open circuit and a short circuit. The next step is to solve the circuit using conventional techniques. I will consider It the total current in this circuit, and I is the current through the resistor R3. I will consider Ra to represent the parallel combination of R4 and R5. That means Ra is equal to R4 times R5 over R4 plus R5. We get 3 ohms. And Rb is given by Ra plus R3. That means Rb is equal to 8 ohms. The total resistance of this circuit is given by R2 parallel to Rb in series with R1. That means Rt is equal to R2 times Rb over R2 plus Rb plus R1. We get 18.18 ohms. The total current in this circuit, It, is equal to Va over Rt. And if we replace Va and Rt with their numerical values, we obtain It is equal to 1.46 amps. In order to calculate the current I, I'm going to use the current division rule. That means I is equal to R2 over R2 plus Rb times It. And if we replace the resistors and the current with their numerical values, we obtain I is equal to 0.4 amps. The voltage V1 across the resistor R3 is given by R3 times I, according to Ohm's law. And if we replace R3 and I with their numerical values, we obtain V1 is equal to 2 volt. Now let's consider the independent current source, Is, active and the independent voltage sources, Va and Vb, inactive, which will be replaced by a short circuit. This circuit can be simplified as follows, where Ra represents the parallel combination of R1 and R2. That means Ra is equal to R1 times R2 over R1 plus R2. We get 2 ohms. And Rb represents the parallel combination of R4 and R5 is equal to R4 times R5 over R4 plus R5. We get 3 ohms. The current I can be calculated using the current division rule. That means I is equal to RA plus RB over RA plus RB plus R3 times IS. And if we replace the resistors and the current with their numerical values, we obtain I is equal to 1 amps. According to Ohm's law, the voltage V2 across the resistor R3 is given by R3 times I. And if we replace R3 and I with their numerical values, we obtain V2 is equal to 5 volt. Now let's consider the independent voltage source VB active and the independent voltage source VA and the independent current source IS inactive, which will be replaced respectively by a short circuit and an open circuit. I will consider I is the current through the resistor R3 and IT is the total current in this circuit. RA represents the parallel combination of R1 and R2 is equal to R1 times R2 over R1 plus R2, we get 2 ohms. And RB represents the parallel combination of R1 parallel R1 and the parallel combination of R1 and R2 in series with the R3, we get 7 ohms. And the total resistance of this circuit is given by R4 parallel to RB in series with R5. We get R4 times RB over R4 plus RB plus R1, we get 8.42 ohms. The total current IT is given by VB over RT. And if we replace VB and RT with their numerical values, we obtain IT is equal to 2.25 amps. The current I can be calculated using the current division rule. That means I is equal to negative R4 over R4 plus RB times IT. And if we replace the resistance and the current with their numerical values, we obtain I is equal to negative 1.425 amps. Now, according to Ohm's law, the voltage V3 is equal to R3 times I. And if we replace R3 and I with their numerical values, we obtain V3 is equal to negative 7.125 volt. After completing the analysis for each independent source while treating the others as turned off, the next step is to combine the results algebraically. This process enables us to determine the overall circuit response. That means the voltage across the resistor R3 is equal to V1 plus V2 plus V3. And if we replace V1, V2 and V3 with their numerical values, we obtain Vx is equal to negative 125 millivolt. After we finish the calculation, we conduct a simulation using the SPICE simulator to verify our results. Now let's proceed to the SPICE environment. This is our network drawn in SPICE simulator. We can see here this is the independent voltage source VA, the independent current source IS, the independent voltage source VB, R1, R2, R3, R4, R5. I connect here a voltmeter in order to measure the voltage Vx across the resistor R3. Let's move on to analysis, DC analysis, calculate nodal voltages. We can see here that Vx is equal to negative 125 millivolt. After completing the circuit simulation, we can clearly observe the similarity between the simulation and calculation results. This serves a validation of our work. Alright, thank you for watching this video. If you have any question, do not hesitate to contact me by email or leave a comment under this video and I will answer you as soon as possible. If you like this video, don't forget to subscribe and share. See you next time in another video about superposition. Take care and bye bye.